Okay. We shall have a recap of like what we have studied in the last class. Like, can anyone list out the classification of systems what we have seen in the class?
Continuous and discrete
Continuous and
systems.
discrete.
So, continuous time and discrete time systems, right? Okay,
Linear and non-linear.
right. Linear and non-linear systems. Okay,
Time variant and time invariant.
time variant and time invariant systems. Okay, next.
Linear time variant and linear time invariant.
Linear time variant and linear time invariant systems, right? Next,
Causal and non-causal systems.
causal and okay, discontinuing context. Causal and non-causal. Next,
Systems with memory and systems without memory.
right. Systems with memory and without memory. We have another names for
Dynamic and static.
right. So system with memory are called as dynamic, and without memory we call them as static systems. Any other number I have told you?
Stable and unstable systems.
Right. Stable and unstable systems. Okay.
Invertible systems.
Invertible systems. Right. Next.
Feedback systems.
Systems. Okay. Having a small recap of the first one, continuous time and discrete time systems. So if every system will have an input and output, okay, and the system is performing some operation on the output, sorry, the input. So if I represent input with x of t and system is performing some transformation, so then the output y of t is understood as transformation applied on the input. Okay, and recollecting the concepts in classroom. So regarding the linear systems, what principle to be satisfied?
Superposition principle.
Superposition principle, right? And superposition principle is also a combination of two properties. What are they?
Additivity and
Additive and
homogeneity.
Homogeneity.
Right. Additivity and homogeneity. Okay. What is additivity? So if I have a system and I have applied x1 as an input, received y1 as an output. for the same system, I have applied x2 as an input and received some output as y2. Then if the input is a sum of x1 and x2 and the response observed is y1 plus y2, then what property it is?
Additivity.
Nice. So if this is true, that means additivity property is satisfied. Nice. What is homogeneity? Have a same system, and if any signal is multiplied with a constant, then in the response output, if it is observed that it is a1 y1 of t, then homogeneity property is satisfied. That means the earlier recorded output is multiplied with a constant. Okay, the same constant which we observe in the input, right? So if, for suppose if only additivity was satisfied and homogeneity is not satisfied, or vice versa, only homogeneity is satisfied, additivity is not satisfied, can we say that it is a linear system?
No, sir.
No. Okay, so both additivity should get satisfied and homogeneity gets satisfied, then only we can say that it is a linear system. So combining these two properties, we represent like this. If a1 x1 of t plus a2 x2 of t is given as an input, then the response is a1 y1 plus a2 y2, where y1 and y2 are the individual responses obtained when x1 and x2 are given individually. Okay, so if this is true, then the system will be linear, otherwise it will be non-linear. Okay, I'm not concentrating on continuous time and discrete time systems, because it is very simple that if input and output are continuous in nature, the system is a continuous time system. If the input and output are discrete in nature, then we say that the system is a discrete time system. After that, third one, time variant and time invariant. Okay, which property, which operation on signals we have used here to explain this time variance?
Shifting, time shifting.
Right. So time shifting is a base property we generally use for talking about whether the system is variant or invariant. Just to recollect, so if I say that a signal x1 is given as an input and output is recorded as y1. Now, so this is already recorded. Recorded in this is noted. Next, I am going to give some other signal x2. Now, the response y2 is recorded. Now, for suppose, if this x2 is a time shifted version of x1, then if this response is observed as the same time shifted version of the earlier recorded y1, then is this time variant or time invariant?
Time invariant, sir.
Right, this is time invariant, since we observe the same amount of shift in the input and output. For suppose if this response is like this, y1 of some t plus t naught, is this time variant or invariant?
Time variant, sir.
Right, it is time variant. Even though the number is same, t naught is same, but here if I think it as, if I assume it as a delay, here I have seen it as a delay, but what is this here? It can be considered as advance. So therefore, so this is time variant, whereas this is the example for time invariant. The next one is linear time variant and linear time invariant systems. The only thing is this is a combination of linearity and the time variant property. This is a combination of linearity and time invariant properties. If the system satisfies linearity and time varying conditions, then we say that it is LTV, that is linear time variant. The system satisfies linearity and time invariant properties, then we say that it is linear time invariant systems. Clear? I think till this point we have discussed in the classroom. Am I right?
Yes, sir.
Yeah. We shall go for the next one. There is a causal and non-causal systems and static and dynamic systems, stable and unstable systems. So next one is causal and non-causal systems. Now, just observe this equation. Now, I have a system where I have applied x of t as an input, and the response obtained is 2 times the input signal. What operation the system is performing on the input?
Magnitude scale.
Magnitude scale.
Nice. It is magnitude scale. Now, generally we always say the present time instant. Always, generally, if I want you to count the time, we start from t equal to 0. So I always consider the present time instant as t equal to 0. Now I want to find what is y of 0. It is a present output. Am I right? Give me response.
Yes.
Okay, give me response. I will continue. Yeah. So if t equal to 0 is representing the present time, then as per this, I am representing the present output. That is current output. Now, can you please tell me what happens to the right hand side?
0, sir.
2 times x of 0. It doesn't become 0, but it is 2 times x of 0. Hope you understood.
Yes, sir.
Yes, sir.
Yes.
Okay. So if this, I am seeing it as a present output. Now what will be this?
Present input.
Nice. It is present input. Okay. I'll be going for another example. Second example. So y of t equal to 2 times x of t plus 3 into x of t minus 1. You observe some change, right, for the system. What change do you observe? What change do you observe for this system? This is an example 2 system. We have added this in addition, right?
Yes, sir.
Yes, sir.
Now, shall I calculate the present output? Y of 0. Tell me what happens here.
2 times of x of 0 plus 3 times of x of minus 1.
Right. Now, this we have already mentioned as present output. What is this? Present input. Am I right? Now,
Yes, sir.
what does this become? X of 0 is present. What about x of minus 1? Does it become past?
Yes, sir.
Right. So this becomes past, and since the function is x here, we say it as past input. Now, so comparing these two examples, in this example, the present output is depending only on the present input in the first example. In the second example, present output is depending on present input as well as past input. So these systems, what do you mean by cause? What is the meaning of cause?
Reason.
It is a reason, right? Okay. So here the present output is because of the present input and the past input. So these two are responsible for obtaining this output. That's why we use the word for classifying such systems as causal. Okay. So now we have a name called as causal, right? So the two examples, whichever I have told, the first one is depending only on the present input, whereas the second example, it is depending both on present input and past input. So both are the examples of causal systems. The example 1 and example 2 are the examples for causal systems. Now coming to non-causal system. Now I will give one more example of a system y of t equal to x of t plus 1. Now please find the present output.
Y of 0 is equals to x of 1.
X of 1. Now this y of 0 is the present output. Now what happens to this? What is this actually? With respect to 0, minus 1 is past. If 0 is present, minus 1 is past. What happens to 1? Use the, yeah, exactly. It is the word future. Okay. So if present output is depending on the future inputs, then we say it as a not causal system. Okay. Now I'll be giving you one more example, and you have to tell me whether this is a causal or non-causal system. Can anyone tell me, is this a causal or non-causal?
Casual, sir.
Why? Casual, not casual. Don't use the word casual. It is causal. Now, is this an example for causal or non-causal?
Causal, sir.
But I say that this is non-causal. Can I prove it? So you have checked it for y of 0. It is x of 0. So I have started my timer. Okay. And I have started finding the present output at every timer instant for every 1 second. Now, in that, when the immediately after the timer have started, I have calculated the output as y of 0, and it is depending on the present input at that time. And next, at t equal to 1, after 1 second, I again calculated the present output y of 1. Then it was depending on x of 1. This is also the present input at time t equal to 1. If I go for the next second, can you see that?
Y of 2 equals to x of 4.
X of 4. So with respect to time t equal to 2, does this become future input or present input?
Future input, sir.
Right. So this becomes future input. So not only checking y of 0 or y of 1, we have to go for the other values also, such that whether it is depending on future input or not. So this is the best example for non-causal system. Okay.
Yes, sir.
Yeah. I will give you one more example. So y of t equal to 2 times x of t plus 5x of t plus 1. Tell me whether it is a causal or non-causal.
Non-causal, sir.
This is an example for non-causal, because if you start finding output at the present instant, it's okay that it is depending on the present input, but it is also depending on the future input. So this is an example for non-causal. Now I can now revise here. In the first example, you can see that present output is depending only on the present input. This is said as a causal system. Here in the second example, present output is depending on present input as well as a past input. So there is no rule that it has to depend, the system present output depends only on the past input only. No need. So either it may depend on present input, either it may depend only on the past input, or it may depend both on present and past inputs. So all these are the examples for the causal systems. Whereas now in this example, in the fifth example, the present output is depending on present input and the future input. So this is an example for a non-causal system. Now I will introduce one more new word. Can you see this, what I wrote?
Yes, sir.
Okay, it is anti-causal. So when the present output depends only on future input, okay, then we say that system as anti-causal, only on. Whereas here in the example 5, we observe it is depending on the present input as well as the future input. So this is an example for non-causal. Even anti-causal systems are also said as a non-causal systems because we observe the dependency on the future output. Okay, hope you got the idea about causal and non-causal systems.
Yes, sir.
Yeah. What is the next one?
System with memory, systems without memory.
Right. So the next one is systems with memory and without. And without memory, we call them as static. And with memory, we call them as dynamic. Now, I have quoted some examples earlier. The same examples I will quote here also. Right. Can you see this second example which I have told or explained regarding the causal systems? Can you see this example?
Yes,
Yes,
sir.
sir.
Yeah. So present output is depending on the present input. It is good, but the system should store one of the past input. Am I right here?
Yes, sir.
Yeah. So that means the system needs a memory. So this is an example for system with memory, dynamic, right? It is dynamic. Whenever it is needing to store either the past inputs or the system needs to store some future inputs, we call it as a system with memory. Hope you got me.
Yes, sir.
Yeah, I will give an example for static. Y of t equal to 2 into x of t. This is static because there is no need for memory. Present output depending only on the present input. That's it. No need for storing any past values of the input. Now, y of t equal to 2 into x of t plus 3 into x of t minus 1 plus 5 times x of t plus 2. Now, can you see the dependency on the past and future values of the input? Here, is this past or future?
3
This
times x of t minus 1 is past and the
is
other one
past.
is future.
Okay, so this one is future. So there is a need for the system to store the past input and the present input. So that's why we call such a system as a dynamic system, which needs a memory to store the values. I will quote one more example here. So y of t equal to 2 times x of t plus 2 into y of t minus 1. Hope you are seeing what I wrote now.
Yes, sir.
Okay. Uh, I wrote something new. This you can easily tell. This is a
present
present
input,
input. This one,
past input,
nice. And what about this?
past output.
Exactly. So it is past input. So whenever we observe some systems, which also depends on the past outputs. So this can also be said as dynamic systems. Got it? Is it clear?
Yes, sir.
Even I can add here this one, okay, because I can't go for uh, future outputs. Future outputs we can't get right now. Now this one is, so all these dependencies will come under the dynamic systems. Wherever the system needs a memory, we say it as a dynamic system or system with memory. Whenever the system doesn't need any memory, that is depending only on the present input, then we say that the system is static. It is without memory. Clear?
Yes, sir.
What is the next one?
Stable and unstable systems.
Stable and unstable systems. So here, I want to stress on BIBO stability. You don't know this actually. So this BIBO stands for bounded input and bounded output. Before going into the stability, you have to know what do you mean by bounded. Okay, I'll give you an example for that. Now, example. What is this signal I have represented here mathematically? U of t.
Unit step signal.
Nice. Unit step signal. What values does it take?
1, 0, 1.
Yeah, it is either 0 or 1. Am I right?
Yes, sir.
Are these finite values?
Yes, sir.
Yeah.
Yes,
So that
sir.
means the values of u of t lies in between 0 and 1. Am I right?
Yes, sir.
So this boundedness representing the bounds of the value of the function, not the time bound. Hope you got me. If I'm thinking about time bound, what are the time limits for u of t?
Minus infinity to
Yeah,
plus infinity.
u of t you can always think about the infinite limits. But here boundedness is always relating to the value of the function u of t. Not only u of t, value of any other function. I have quoted this example to say that the value of the function u of t lies in between 0 and 1. That means its value is lying in between some finite boundaries. That is why this unit step signal is a best example for a bounded signal. Am I clear?
Yes, sir.
Yes, sir.
Now, just I want to make you clarify about boundedness. Now tell me, is this signal bounded or not? Sin t.
Yes, sir. It's bounded between -1 to 1.
So S it is bounded. So the value of sin t always, because I made it modulus, its value always lies in between 0 and 1 because I made it modulus. Okay. Or if I want to see the values of sin t, it will be oscillating between -1 and +1. So its values are bounded between the finite values. -1 is finite, 1 is also finite. Okay, so that's the reason sin of t is a bounded signal. Now, coming to the classification, I have a system. I have given an input x of t, which is bounded between some finite limits. Clear till this point?
Yes, sir.
Now, I am now trying to observe the output of the system, and I have observed that this y of t is lying in between m3 and m4. These two are also finite values. M1 or M2 are finite for the input, and for the output, M3 and M4 are also finite. Okay. Now, the input applied is bounded, and here the output, since its values are lying in between the finite values, output is also bounded. So, in that case, if we observe for an applied bounded input, if we observe the output obtained is bounded, then this system is satisfying the condition of BI/BO stability. Got it?
Yes, sir.
Yeah. Now, I want to show you one more example. I have a system applied the same bounded input, and I have observed that the value of this output y of t lies in between 0 and infinity. Now, is this a bounded output or an unbounded output?
Unbounded outputs.
Bounded.
Unbounded. Why? Because of the presence of a non-finite value. So, this system is not satisfying BI/BO stability. So, this can be said as an unstable system. Clear?
Yes, sir.
Yeah. Now, one point I want to mention, you can see the limits here, M1 and M2. But you can see a different input, different range here, M3 and M4. Okay. So, there is no rule that this y of t lies in between the same limits, like M1 and M2. The only reason that we have to think about is whether they are finite or not. Then we say that the system is BI/BO stable. So whenever we are talking about stability, we always talk about bounded input, bounded output, stability in the case of systems. Okay. What is the next system?
Invertible systems, sir.
Right. Invertible. Now, listen carefully. I have a system, one, okay, and this system one is given an input of x of t, and this time this system is performing some operation t on this x of t, okay, and this system is now connected in series or cascade with some other system too. Now, what is the operation of this system? This is performing the reverse operation of so-called output, whatever you have obtained. And then the meaning is here y of t is transformation applied on x of t. Okay. Now what I am doing here is, if I apply the inverse transformation on the output, I'll get x of t. The reverse option, reverse operation. That means if this performs scaling by a factor of as an example of x of 80. Now this performs an operation of t by a. Is this a reverse operation or not?
Yes, sir.
Okay, right? So maybe I can write it as y. Y of t is x of 80. Whereas again, this system 2 is performing the reverse operation of the first operation. Then what is the output that you'll get? The output is same as of your input. Is this clear or shall I repeat? System 1 is performing some operation. System 2 is performing a reverse operation. And both systems are connected in series or cascade connection. Okay. And after the system 2, you see that the same input is observed. So now the definition of invertible systems comes like this. So a system is said to be invertible if there exists an inverse system connected in cascade to it to get the response same as the input. Can you read it again once again? A system is said to be invertible only if there exists an inverse system connected in cascade to it to get the response same as the input. So now you see two systems, am I right?
Yes, sir.
Yeah, system 1 and system 2. Now you have to tell me which one is invertible and which one is inverse.
System 1 is invertible, system 2 is inverse.
Right, system 1 is invertible, system 2 is inverse. Okay, right? Now what I am doing is I am now connecting system 2 first and then having a cascade connection with system 1. This performs t by a as I said earlier, and you get y of t here. This is x of t, and here it is performing y of 80, and you get the same output. Now tell me which system is invertible here?
System 2, sir.
Exactly. So always the first system which is connected here, and there exists a second system which is connected in cascade to get the output same as your input. So the second system will become inverse. So it is all about the order we connect. So if there exists an inverse system, then only the system 1 is said as invertible. If there is no system which gives the inverse operation, then I can say that this is a non-invertible system. Got it? Is it clear?
Yes, sir.
Yeah, okay. So to say that a system is invertible, then there should exist a system, another system which performs an inverse operation to it, and it is connected in cascade. That is how we have a classification such as invertible and non-invertible systems. So in the definition, a system is said to be invertible only if there exists an inverse system which is connected in cascade to it to get the response same as the input. If inverse system doesn't exist, then the system is a non-invertible system. Hope I'm clear. And last one. Is feedback systems. I think I can draw a system here. Now can you see the system now?
Yes, sir.
Okay, right. So you observe that maybe I can represent here also system, or I don't want to confuse you. I will do what I can. This entire system is called as a feedback system, where the output received here, you can see here you received output, right?
Yes, sir.
Okay, because of some operation, maybe I can say it as some operation, you received some output, and that output is fed back. Maybe you can have a gain of some A to the input again, and it again calculates Y. So every time the Y changes. So here whenever we observe a feedback connectivity, output is given as one more input, as one of the input contribution like this. We say that such systems are feedback systems. Uh, any doubt in this classification of systems now?
No, sir.
Okay.